This afternoon, we're going to be talking, Addie and I will be talking about Lunar-VISE, which is our upcoming NASA surface science mission to the moon's Gruithuisen domes. And so just to give a little bit of background about myself, my name is Kerri Donaldson Hanna. I'm an assistant professor in the Department of Physics, mostly working in the Planetary Sciences group. And since my arrival in March 2019, I've been a part of several teams that have been successful in obtaining research funds from NASA, including UCF survey node that many of you may have already heard of called CLASS, which is led by Dan Britt. And I'm also a co-investigator on 2 missions going to the moon, L-Series and Lunar Trailblazer. And recently I PI'd the Lunar-VISE PRISM proposal that was selected and that Addie and I are going to be talking about today.
And I'm Dr. Adrienne Dove. I'm an associate professor here in the Department of Physics, and my research focuses on dust dynamics and plasma surface interactions, both on planetary bodies and on spacecraft. I am, Kerri mentioned earlier, the survey class node that we have here at UCF, so I'm the deputy PI of class, and I'm also the deputy PI of Lunar-VISE. And some other projects I've worked on since I've been here have been a couple of CubeSats. So SurfSat was a CubeSat that I led that launched in September 2018. That was actually UCF's first flown CubeSat. And I'm also PI and co-I on a number of projects that build instrumentation to fly on parabolic and suborbital flights, as well as International Space Station flight experiments. So today we are going to give you a little bit of background about the Artemis set of missions, and also just sort of in general NASA's plans to return to the moon and to go forward to the moon. And then we'll talk about our specific PRISM mission, and then we'll talk a little bit more about some of the logistics of our PRISM proposal and how some of that was done here at UCF. So first, a little bit of background about the missions that we're going to be talking about. So Artemis is NASA's big grand plans to return to the lunar surface with both humans and robotic exploration. So this slide sort of is a nice overview that highlights some of the plans for going forward in the next decade and how we're going to return to the moon. So you can see that the sort of in the top of the graphic on the swoosh shows the different Artemis missions, which includes Artemis 1, which is supposed to launch later this year. That is will be a human mission to sort of go around, or Artemis 2 is the one that's going to go around the moon. Artemis 1 is going to be just an uncrewed spacecraft. And so these will be flying sort of exploratory missions, and eventually we will be landing on the surface of the moon. In the meantime, there's actually a lot of these smaller missions that are returning to the surface that are primarily robotic missions, and they're going to be led by NASA and a lot of the commercial partners that NASA has been building. So this is through the commercial lunar payload services and a number of different opportunities that NASA is doing via proposals that scientists like us can propose to have instruments and missions that go to the lunar surface. You see here on the bottom left, a bunch of the early missions are actually going to the South Pole, and that's because the South Pole is of interest for lunar exploration for resources. It's an area we haven't explored, but we think there's a lot of potential resources there, and it has interesting possibilities for the long-term lunar habitation. So you see a lot of missions going to the South Pole, but then there are also missions going to other places on the lunar surface. And NASA, as I mentioned, is working with the commercial lunar payload services, or CLPS, to deliver a lot of these payloads. This is a fairly unique way of operating that NASA has been working on over the last few years, where NASA partners with commercial providers and differently than in the past. So NASA's always worked with other commercial partners to build spacecraft, but it was always driven by NASA requirements. In this case, there's a lot more left to the providers themselves to do the development, and then NASA sort of buys spots on those landers or purchases their services. So it's actually a very different operation mode. And so these landers are going to be delivering NASA payloads, but they might also have different commercial payloads on those landers. It's up to the providers and sort of how much space they have available. Some of the providers are listed here, and this is the ones who have gotten contracts through NASA. There might be others in the future, and some of these might be in different phases in their development as well. So this graphic is nice because it shows us the lunar surface and where some of these missions are going. I mentioned previously that a lot of them are going to the South Pole. So you can see down there in the bottom, there are several scheduled missions to different places in the South Pole. You can see that there's several missions scheduled for 2023. And this is sort of the onset of a lot of these missions from different providers. I circled the delivery site to Hayworth Crater because Kerri and I both are on projects that are going to be on that lander. And there are a number of other sites then by a number of providers. The one we'll be talking about today is not a South Polar lander, but it's actually up here in the Gruithuisen domes, which you can see sort of in the middle of, nicely in the middle of the image. And these are chosen through different types of proposals and solicitation calls. And we won't talk in too much detail about all of those different ways you can sort of get an instrument onto the moon, but there are a number of different types of calls that we are happy to talk with you more about as well. Do you want to talk about? So in general, the one of the programs is the Payloads on the Surface of the Moon, or PRISM. Program that NASA has developed to have science-driven suites of instruments, and as well as some technology development payloads that are proposed by PIs who are leading the science, and then partner with companies and other industry representatives, for example, to build science suites, but that will address goals related to the moon. PRISM is interesting because the solicitation outlines what the sites will be. For now, they've outlined what the sites will be and sort of what science they're generally interested in. And so you have to do proposals that are responsive to those goals. And then after the suites are selected, teams work with NASA to pick lander and rover capabilities that are required. And then NASA will actually solicit these CLPS providers that we mentioned to provide rides. So they're not predefined which lander, thus far, they haven't predefined which landers or rovers you might go on when you go to the lunar surface. So far, there have been 4 landing sites selected through 2 different PRISM calls. So the first PRISM call was selected about a year ago, and the PRISM 2 call was just recently selected. These are to Reiner Gamma and Schrodinger Basin. Those were for the first 2 PRISM missions that were selected. And then more recent selections are the Gruithuisen domes, so Lunar-VISE, our mission, and an interesting space biology application, sort of CubeSat-based instrument that's going to be going to the South Pole or orbiting. I'm not actually exactly clear on how that's going to operate. But so there's 4 different landing sites that have been chosen thus far through the PRISM program. And we highlight ours here, which is what we'll talk about next.
So of the landing sites that Addie showed, most of these sites were chosen based on workshops that were led by the lunar scientific community to identify high priority sites that would also maximize the scientific return, because NASA understands that we just don't want to put instruments on the moon. If we're going to go to the moon, we should also get science, because that's really important as well. And so the Gruithuisen domes are of particular interest because early telescopic and spacecraft observations showed that these domes were quite unique from their surroundings. And you can see in this image here, these kind of 2 circular features. Those are the domes that we're talking about. And we can see just based on their morphology or their shapes that they stand out from the surrounding volcanic flows. And these early observations also suggested, and their morphology suggested, that the magmas that form these volcanic domes must be highly viscous and enriched in silica. Now, why this is interesting is that on Earth, the only way you can get such silica-rich magmas requires water and plate tectonics. So as an example, if we think about most volcanic features on Earth that are along the subduction zones, something like Mount St. Helens, these are all silica-rich lavas. But on the moon, there is no water, or at least not a lot or high abundance of water, and there's definitely not plate tectonics. So then the big question about how these features on the moon formed is, how did they get there? If there isn't plate tectonics and there isn't water, what processes would you need to form these types of magmas or rocks? And so to better understand how these rocks may have formed, we need to know their compositions and chemistries. And so our main goal with Lunar-VISE is basically to determine the composition of rock that's making up these volcanic dome structures and to characterize the regolith properties as well as the rock properties. We are proposing to land on the top of the dome because it's fairly flat, but the fact that we are going to have a rover that we have access to and that we can put our instruments will allow us to go up to and hopefully map and measure both regolith and rocks, similar to the pictures that we see from the Apollo 15 landing site. And I should note that we have this little rover here on the slide. This is the Lunar Viper rover that will be landing in 2023. This is not the exact rover because we don't actually know what rover will be on. To accomplish our science goals, we're using 2 high heritage multi-spectral cameras that are being built by Ball Aerospace. One is at visible and near infrared wavelengths, and the other is at thermal infrared wavelengths. And then we're also going to have a gamma ray and neutron spectrometer that's built by Arizona State University. And so these 3 instruments will be mounted on our rover, and we'll be able to make several traverses across the dome during a lunar day to really map out and understand the composition, the physical properties, and the heterogeneity in those across the dome. And the nice thing about these instruments is they're a really complementary suite of instruments that will allow us to really map the composition and study the physical properties. I should also note that because we are taking a gamma ray and neutron spectrometer with us built by ASU, if hydrogen is in high abundance in the form of water or OH, we will also be able to map those using the gamma ray and neutron spectrometer system. And then finally, we're going to use our measurements made from the lunar surface to ground truth remote sensing observations that are made in orbit by current and future spacecraft. And so when we're talking about these multi-spectral, visible and thermal cameras, we're choosing the spectral channels that we want to use on our instruments to match those that have already flown on orbital data so that we can make this ground truthing possible. And then in addition to our science investigation, we're also looking to better understand the dust environment of the moon, as well as the geotechnical properties of the lunar regolith, because these are 2 areas of research focus here at UCF. And so using Ball Aerospace built descent and context cameras on the lander, we're going to first image the landing site as the lander is descending to the surface. And this will allow us to characterize how the surface dust gets lofted in responds to our lander. We're also going to use the cameras on the lander to map the geologic context of the landing site, and this will help us plan where we want to explore with the rover. And then we also want to characterize the lunar regolith properties, in particular some of the geotechnical properties, by observing how the rover moves about and interacts with the surface. Now, to successfully accomplish these science and exploration goals, we had to recruit a really large team of scientists that had the right areas of expertise. And importantly, we needed to find institutions that had the capabilities of building high heritage instruments. And so we initially began working with Ball Aerospace, in particular, David Osterman here in the center of our image. And we started working with them because we knew that they had the capability of building multi-spectral imaging systems that have flown in space before. And so the visible camera that we'll be using on our lander and rover have been flown in space before on Earth orbiting instruments. And the thermal instrument that we'll be flying is the thermal camera that's going to the south pole of the moon as part of LCIRRUS. And so we started working with them and started thinking about, if we're going to go to the Gruithuisen domes and we want to address these science questions, what other instruments would we need with those cameras? And so we started meeting with additional institutions to see what other instrument capabilities that they had and whether or not those instruments could fit the payload requirements, meaning did they have high enough technical readiness level? Because these instruments have to be built on a very short turnaround time. And also, did they meet the mass and power budget requirements? So then once we had our entire instrument suite set, we then reached out to scientists to fill expertise gaps that we could see that we had within our team. And then the other person that we also added to the team is that the PRISM announcement of opportunity requires that we have a project manager on the team. And so we interviewed and recruited a project manager, and Javier Benavente as our project manager, and he has experience with NASA project level management. And so
I'm going to talk a little bit more now about sort of how, I'm actually going to skip to a different slide here, about how we developed this proposal. And so Kerri did a nice job of sort of introducing the team and how we selected a lot of the folks on the team. One of the things to think about when we're doing big mission proposals like this, and we're going to touch on this, we were asked to touch a little bit on sort of like how you develop these types of big proposals. So PRISM 2, again, was a second version of this type of proposal that NASA has offered. So they offered the PRISM 1 call a couple of years ago now, and we actually did propose to that call with a similar suite of instruments that was going on a lander, and it was to a different site. So it was to Reiner Gamma, which is a different site on the moon that's interesting for very different, awesome science reasons. But so we had done a lot of the sort of preparation in terms of starting to work with Ball and starting to work with some of our science team members on that previous proposal. So we were in a pretty good state to start working on this proposal then when the solicitation was finally released. I have an asterisk on the timeline, on the name timeline here, because this is most of the timeline from when the solicitation is released to when we found out. But as I just mentioned, there was some preparatory work that was done, and Kerri mentioned earlier, with figuring out who we were going to work with and starting to find our main instrument leads before we actually did a lot of the preparation that's listed here. And the solicitation was released around September 2nd. There was actually, like it's mentioned in the NASA sort of overall science mission directorate call from like when it's out in February. So we knew there was going to be one, but there weren't details about like what the landing sites were going to be or what the payloads were going to be able to sort of accommodate until the September release of the solicitation. So the way PRISMs work is, again, is that NASA will sort of release a solicitation that says, here are the landing sites that we are going to allow you to propose to this time, and some guidance on things like what vehicles you'll be able to go on. And so for this call, it was that there was going to be an opportunity to have a lander and a rover at the Gruithuisen domes. The South Pole site, there was only the lander opportunity, but you could propose to include a rover on your own. So that opened up a lot of doors for us in terms of being able to think about how we would accommodate our instruments. And it also changed a little bit how we looked at developing our science and our ConOps for how the mission would be run. So the solicitation was officially released on September 2nd. We were working on our sort of official team formulation, sort of August through October. You have to have the majority of your team outlined by the time you submit your step one. So the way these NASA proposals work is that there's a step one, which is saying, I'm going to propose to this. Here's the general synopsis of what I'm going to propose. And that is due usually a couple of months before The step 2 is finally due. And then, so you really want to have your team in place for a number of reasons, but also because you have to put them on the step 1 proposal by this October 22nd due date. At the same time, we were starting to work on formulating our team and figure out who would be, as Kerri mentioned earlier, the instrument leads, the science leads, figuring out who our project manager would be. We were starting to work on thinking about, okay, what are all those budgets going to look like? Do we need to get NDAs in place with Ball Aerospace, with Arizona State, with other folks involved on the team? So there's a lot of sort of that background work that's not even related to writing the text of the proposal that has to happen. And you really have to start early on all of that because different processes at different institutions and here at UCF can take a long time. After that, it was really hard working on the science and the technology. So there were different lines of work working on sort of the science and the investigation, what science we wanted to be able to do and how we were going to do it, and then how the instruments would be responsive to that. We had sort of some internal deadlines, which are sort of here in red, that are the science baseline text and our science traceability matrix. So this is a thing that must be included in the proposal that outlines what your science and your technology requirements and drivers are. And it's also a really good way to just sort of like make sure you understand what you're saying, you're proposing, that your instrument's responsive to that, and that it all holds together so that the rest of the text of your proposal supports that in a lot of ways. We did then do a red team review in late November with folks who were knowledgeable about the instruments or the science from outside of UCF, and that was led out of Ball Aerospace. And then internally, we had obviously our own internal UCF deadlines. We were working with the folks at Cost Pre-Award and OR prior to this for those budgets and NDAs and all of that stuff. But we had to start getting our initial documents in the beginning of December and our final documents in then on December 14th. And the proposal was submitted on December 16th because UCF was going to be closed on the 20th. And also, it's just good to get it in on time. But then for the next 6 months-ish, we just twiddled our thumbs and nervously chewed our fingernails, waiting to hear back. Also during this time, obviously, there were all of our science team meetings, a lot of meetings with like Ball Aerospace and instrument providers working out a lot of nitty-gritty details. And so looking at that timeline and how we developed the team, Kerri mentioned the team that we have here. I wanted to just bring up sort of our this chart that shows sort of the organizational structure. So obviously this is led out of NASA, but then Kerri, as the principal investigator, is here at UCF, and I'm the deputy PI. I'm here at UCF as well, and we oversee the science team and sort of the rest of the structure of the group. We do have a project manager who is local in Florida, but not here at UCF. That was because we just don't have those resources currently here at UCF. And we then also have resources for project engineering, payload development, lander, INT, and some of the different facilities that are spread out through Ball and ASU and LASP. I will highlight something we haven't mentioned yet, which is that we also have a really strong education public outreach program that is led here at UCF with our co-I Adam LeMay, and will involve undergraduates and some K through 12 outreach and education that we're really excited about. So you can see through the structure that a lot of it is led here at UCF, and as Kerri mentioned, the instruments and other things are developed at ASU and Ball. Part of that is that's where those instruments that have high heritage have already been developed. We don't currently have those facilities here at UCF. I say currently because that's obviously a hope for the near future. But I wanted to highlight that a little bit just to show the things that were specified that were needed. So the PRISM call said that we had to have a PI and a deputy PI, and we had to have a project manager. That was actually sort of uniquely specified in this type of proposal. That's going to vary between different solicitations. But then obviously we needed instrument sciences, science teams, and all of the other folks to support the mission. Some of those folks are here, but a lot of those folks are at mission operations centers at LASP that's been developed, at ASU that have been developed to already work with other missions. So long-term, we would love to have mission operations and facilities like that here, obviously. And then there's a lot of facilities that will be using at Ball, at LASP, at Colorado, and at ASU to do the hardware development, to do integration, to do testing, and then the long-term mission operations and data support. So most of the stuff on the right in the hardware and facilities are things we don't currently have here at UCF, but we are working more toward developing and figuring out how we can have that kind of thing here to be able to have a lot more of the mission in-house. And I think in interest of time, I'm going to stop there.